All right, here we go, exponential functions. Lots of rules for you if you would choose to follow them. They are basically shortcuts, I believe, because obviously you could write them out as what they actually stand for, and it would work out the same way. What I mean by that is obviously on this first one you could use shortcuts, but really what the top is saying, the numerator is saying to do that. Denominator is saying to do that. Basically, if you wanted to, you could do it that way. And it ends up being 3 to the 1, 2, 3, third. Okay. What the shortcuts allow you to do is do that in a much quicker fashion than writing them all out. But if you ever do get confused, you can just write them all out. But what it says is when you divide, basically if you look right here, it'd be this one. What you can do is take the numerator exponent and subtract the denominator as long as the bases are the same. They're both a, right? And so my bases are the same, so I could simply, in this case, just write the 3 and then do 5 minus 2, and you see how you get 3 to the third anyways. As far as I'm concerned, that's simplified. If you really want to write 27, that's fine. That's completely up to you. But as far as I'm concerned, same thing here. Again, on this one, if you really felt like it, you could write it out. Right? That's what it's saying. Here's your 5 squared. There's your 5 to the third. Right? So in other words, 5 to the fifth. Or you could use this one right here, which says if your bases are the same, you can just go ahead and add the exponents. The key there is the bases do have to be the same. In both of those cases, A and B. Everybody good? All right. Letter C, you might wonder, well, how am I supposed to write that one out by hand? Well, you still could if you wanted to, because it's 7 to the third, right? So, right, there's one of them. You could kind of maybe group it like this if you wanted to. Right, there's 2, 3. The only reason I'm putting the parentheses in is to make sure that I put them all in there, right? So it's 7 to the third each time, and I did 4 of them. So in other words, it's 7 to the 1, 2, 3, 12. Or as the shortcut says, if you have a base that is then a power to a power, either way, doesn't matter which way it is, you can just go ahead and multiply. So you write down the base, 3 times 4 is 12. Because isn't that really what we did here to figure out how many were there? We knew there were 3, we knew there were 4 bunches of them, might as well just multiply, right? Okay. But do you see how if you ever really get stuck, you can just stop and say, wait a minute, what does it really mean? Okay, so 7 to the 12. 2/3 to the second. The reason that I put this one on here is to show you that if you have a fraction, it's not necessarily really something to get too scared about. You can just take the numerator to that power and the denominator to that power as long as you're supposed to take the entire fraction. Realize how that and this are different. Big difference, right? On the one on the left, they want the entire fraction taken to the second power, where the one I have in blue, it's just the 2. Okay, big difference there. So this one, the one that we have written here, is basically, just take the numerator to that power. Well, 2 squared is 4, and then take the denominator to that power, which is 3 squared is 9. Okay, no big deal on that. If you ever need to, I'll just make the distinction here. Not that it's necessarily going to help you right away, but if you do that, it's the same thing with square roots. You can, if you want, take the square root separately. It may end up helping you, kind of like we did with square root of 2 over 2 when we did that on the unit circle and things like that. It's kind of how you come to that. Yep.
Is it okay if we leave it 2 squared over 3 squared or no?
That's okay. The question was, can we leave it 2 squared over 3 squared? That's probably all right. But my purpose there was to show you that you can just square the numerator and square the denominator. So, okay. All right. So, any questions on A through D? All right. Well, we got a few more to work on here. I'm actually going to show you something about letter E. I've always thought about teaching it before now, but I think it just confuses too many people, so I haven't. This one you cannot use that rule. Why? Bases aren't the same. But remember, I asked this a lot in advanced math. Can we get them the same? And we can. So that's one way you can do this, because 4 can be written as 2 squared. Agreed? But that is just the 4 part, right? That still has to be squared. Do you see that? That's a lot of 2's. I probably should have picked a different number. So in other words, this is really 2 to the 4th, 2 to the 2nd, right? Excuse me. Now my bases are the same, correct? See that? Now I can use that rule that says write it down. And what do we do with exponents in this case? Okay, is that what it says? Are you sure? Yep, all right. So you add it, 4 plus 2 is? Now, does anybody know 2 to the 6th? I just want to make this note so that when I show you the other way, you'll understand. I heard it. 64. Okay, so do you agree that, I know I told you 2 to the 6th is fine. The only reason I did 64 is so that I can show you the other method of doing this one. Okay, so everybody's good. Get the bases the same, and then you can use a lot of those rules, right? Another way to do it is, if you have exponents the same, there's another way you can do it. Are my exponents the same? Okay, so then just write down the exponent. And then do whatever it says to do to the bases. What's it saying to do to the bases? What's 4 times 2? Is 64. Okay, a little bit quicker. Okay? But you have to remember that when the exponents are the same, write it down, just go ahead and do whatever it says to do to the bases, which it tells you to multiply. 4 times 2, 8. A lot quicker. Okay? All right, letter F. Whoa, we got a lot going on there. Guess we'll just do it this way. Let's just kind of forget about that one for now and just do the problem that you see. So in other words, it's 5 to the 3rd over 2 to the 3rd, right? But I have to take that to the 2nd power, right? Agreed? So in other words, it becomes 5 to the 6th over. Okay. Or one thing you can do Can you do that? Could we have done that quicker right from the beginning? Yeah. I'm trying to show you how to manipulate things, I guess you could say, legally. All right? You can do that. Okay? You could have just said, well, it's 5 halves to the, just multiply, it's power to a power, 6. Okay? Now, are my bases the same in letter G? Is it quick to get the bases the same? Or is that going to take some work? Okay, what base can I get to? I can get to, well, no, we're going down, so 2 is the base. A lot of people think you can get to a base of 8. But remember, 8 squared is not 16. All right? So you can get to a base of 2. I'm on letter... Oh, you do? What do you have? You have an 8 and 7? Yeah. Well, let's do that problem then. 8 squared times 7 squared. All right. Now let's start the questioning over. Can you get the bases the same? No. 7's prime, so... All right. So really, as far as simplifying, you have to go back to the second way I showed you on this one, because the exponents are the same. So write it down. What am I going to do to the bases? I'm going to, so I get, no, that's not something we're all just going to know off the top of our head, so let's just leave it as 56 squared. All right. So what do you suppose I'm trying to, now do you have the same letter H, or is that different? Okay. What do you suppose I'm trying to get across with letter H? Could you get the bases the same? Yes. Sure you can. that the quickest way to do the problem? No. Because the bases aren't the same, but what are the same? Exponents. And what I told you, it works the same as that does over there. Write it down and do whatever it is you're supposed to do to the bases. And what am I supposed to do to the bases here? I'm supposed to divide. Well, does 32 divide by 8 nicely? Well, it does, which is great for us. It is 4 to the 4th. That takes a lot less time than getting those bases the same. Okay. Or, of course, you could write what that is. My key here is getting you to manipulate those bases so that you can work it out the quickest. Yes, question? Okay, the question there is a very good one. It kind of goes back to this one that's kind of really all messed up because you have a different problem than I do. But the question basically said, what if it's 7 to, say, the third? Can we get bases the same? Can we get exponents the same? We could, just not very easily. It'd be a pain. Okay, really any simplifying you can do there, there really isn't any way to manipulate that problem. Okay. So if you were to ask to simplify that one, I would pretty much say that it is. I mean, that's as good as you can do simplifying unless you type that into a calculator. Or happen to know what 8 to the third times 7 to the third, yes, 8 to the second times 7 to the third is on your own. Okay. I'm more concerned about you being able to manipulate exponents and bases. Okay, but great question. Any other ones? All right. So here is one of the things I had you do in advanced math because of what comes after it. And basically says write each expression in the lowest base possible. There'll be some problems I'll tell you what base to use, but on these I just want you to go as low as possible. And what I mean by bases is, well, 16 is the base in letter A, right? Do you agree that I could write 16 as 4 squared? But 4 is not the lowest base I can get for 16. I can do 2. It's 2 to the 4th. Okay. Now those of you that still have your notes from advanced math might want to get your chart of powers out because it might be helpful with this. All right. So 16 is 2 to the 4th. You agree with that much? But I have to take that to the 2x power, correct? Now what did we just learn on that previous couple of slides is that whenever it's a power to a power, you get to, does it matter if there's a variable in there or not? No, you still just do the same thing. It just looks different. So it's 2 to the 8x. That's as good as you can do. There you go. That's what I want you to be able to do. So 16 is one of those, and 64, there are certain numbers that you have a lot of options. But most numbers are pretty straightforward. For example, letter B, I think when you look at 25, I'm hoping that you see that base right away. And the best you can do for that base is, obviously, 5. And obviously it's 5 squared, right? Which then and some of you probably just jumped right to this answer, which is fine. But I just want to show you where it's coming from. Then, of course, we're going to take those two, multiply. So it is 5 to the 6th. So it's okay to not have a variable. It's okay to have a variable. You still follow the same rules. Fractions are the ones that get a little interesting. Does anybody remember how to deal with those? It's technically an algebra 2 technique. Okay. It's to the negative power, exactly. Because basically what it is, you could write it as 1 over, well, what's the base for just 27? If that's all I gave you, you would use 3, right? Right? That's what you would do? But we don't want stuff in the denominator. So unfortunately, you do have to, again, what I call, this isn't something you're going to hear in college, but make it unhappy. Right now, 3 to the third, this 3 at the bottom is happy because the exponent's positive, right? Well, we're going to put it upstairs. We're going to make it unhappy. That's just too bad. Right? You've probably heard your parents say that a lot. That's just too bad. So it's 3 to the negative third, correct? That's how you make it unhappy. And I don't know why there's a little dot there. I'll try and get rid of that. Right. To the 4x. Because now I've got that base kind of on the level it has to be. And so you write down that 3. This is this one. And then what do you do here? Yeah, that doesn't change anything after that. You just had to get it to where you could work with it. And so it is negative 12x. You still just multiply. All right? Okay, so why don't you try letter D right now on your own real quick. Again, go to the lowest base possible. That might be the part that takes the most time. All right. Would anybody like to share what they got? 2 to the negative 24th, I've been told. I agree. Okay. Because 64 is really 2 to the 6th. But then you make it unhappy, so it's 2 to the negative 6 to the 4th, so 2 to the negative 24th. Good? And then we come to the reason that we do all this work with manipulating bases. Because sometimes when there's a variable in the exponent, you can solve it by getting the bases the same. If you can't get the bases the same, you need to use logarithms. But luckily I gave you a 4 and an 8 as your bases. Now if you love logarithms, you can go ahead and solve this one that way. But it's probably not the quickest. Now, does it say right here that you have to get the base as small as possible? No, it doesn't. But too many people in the past have told me I'm going to write 8 as 4 squared to get the bases the same. But 8 is not 4 squared. But you can see the mistake that they made. Obviously 4 squared is 16. That's not what I have. So unfortunately, in the one I gave you, we do have to work on both sides. And the base we're going to use is 2. So this is 2 squared, right, to the 2x. And 2 to the 3rd to the x plus 1. Now, most students on the left side don't have a problem with that. It's basically 2 to the 4x. It is very easy to do the right side incorrectly. Okay, it's 2 to 3x plus 3. You have to distribute that 3 through that expression. Okay? Now, why do we do all this work to get the bases the same? Yeah. How come I can cross them off? Yeah, at this point, does it matter? Whatever exponent I end up with here better be the same here if it's 2 to that power, right? They better be the same. Otherwise, this isn't going to work. All right? Those exponents have to be the same if they're going to be equal, so you can just get rid of them. And then just solve the problem that we've been solving since Algebra 1 at the latest, perhaps before then for some of you. Okay, because now that 2 doesn't matter anymore. So you subtract 3x, and so x is 3. And again, what that means is if I were to put 3 right there and 3 right there, I'd get the same thing. And you do. Okay. Or yeah, you could throw them back in here if you wanted to. But I like to go back to the original, because what if I made a mistake on this first step? It's probably still going to work, because I did the rest of it probably right. So I like to substitute it in here, way back to the original, just to make sure. Okay? And there you go. Questions on that? Okay, why don't you go get a graphing calculator, please? I think you should know where they are by now. Okay, here we go. We are going to graph y equals 3 to the x minus 2. This is something that perhaps you do not have a general idea of what this looks like, but I hope by the time we are done with this particular section, you have some idea of what these exponentials are going to look like. Whether it's a variable in the exponent, it was probably the ones that we're most concerned about. Because, let's face it, you should know x squared, x to the 3rd. You should know all those by now, have some good idea. Or even 1 over x. But having the variable up there, we haven't really dealt with exponentials all that much. Okay, and obviously we want the 0 or zeros, domain and range when we're done. So, again, probably a good idea to start off here, because who knows who was messing around with that stuff before you used this calculator. It could have been me. And quit out of there. Again, we want a graph, so y equals is probably the place to go. So we want 3 as my base to the x power. Yeah, you got to use that caret key. Yeah, and make sure you hit this x right here. And then minus 2. Okay. And just so we have the same thing, let's just all zoom standard just so it at least looks the same when we all graph. Because I'm pretty sure that some other classes are kind of messing with the window a little bit. So if we all just zoom, and then the 6th one down, just scroll down, or just hit 6. It's going along, and whoa. All right, it's gone. Exponentials will either look like this or obviously curve down the other way if it's a negative exponent. If you want to know when exponentials happen, a lot of time, growth and decay is exponential. It will start, population growth for one thing starts off. They're okay approximations, but the problem with populations is they do balance off because there's only so much carrying capacity. Exactly. So they do, it's a logistics equation. We'll talk about that some other time. But this is a pretty good approximation of growth of how something like that would happen, or decay would obviously go the other way. Okay, that's what exponentials are going to look like. They're basically going to go just fine for a while and just take off, and they're gone. Right? And so now what it says is to find zeros in domain and range. Okay. Well, maybe let's start with domain. If we start on the left side here, do you think there's any problems over here? In other words, are there any x values you can put in here that aren't going to give you a y value in the end? Can I put negative 1 million in here for x, and will I get a y value? I will, won't I? All right. And so we know that we're going to be fine there. How about positive 1 million? Can I put positive 1 million in here for x? It's going to be a huge number. And that's why it'd be way off this graph. All right. And so domain, basically, as you go left to right, are there any problems? No. So domain is obviously someone's favorite answer. Negative infinity to infinity. How about range? That's possibly one that could be a problem. You might have to look at your table to kind of see what's happening. Okay, so take a look over here. Table. All right. So, well, which way should I go to kind of try and figure out what's happening? Go up, yeah, from here. Because it's the negatives that we're concerned about. Got the idea? Now, the thing is, the reason that happens is if I put a negative in here, it kind of talks about what we did before, right? It really means, let's say I'm putting 14 in. It really means 1 over 3 to the 14th power. Is that a really big number or a really small number? Incredibly small. Agreed? And then I'm going to subtract 2. Agreed? That's what we would do here. And so no matter what I do, it becomes a very, very small number. But the calculator is somewhat lying to you. Is this value 1 over 3 to the 14th minus 2? If you actually had to calculate that by hand, it'd be a pain. But does this actually equal negative 2? No. What'd your calculator do then? Kind of cut off, it rounded the best it could, right? So does negative 2 actually get graphed here? No. Because no matter what number I put in here, right, if I put, say, negative 100 in there, so 1 over 3 to the 100th is at least some positive value, agreed? It is very tiny. And then minus 2, do you agree, is not going to equal minus 2, or negative 2, right? So negative 2 doesn't get graphed. How about negative 1.9 with a million nines after it? Does that get graphed? Okay, so let's think of our interval notation. What's probably the easiest way to do that? Well, for range, say that it doesn't include negative 2, but does include pretty much everything else, right? Because as you go up, everything else gets graphed, and in a hurry, all right? And so all the way to infinity. You may notice what I've been trying to show you this year so far is, in a lot of my classes, is somehow how this calculator is only so good. You got to sometimes look at that function and think about it. Okay? I'm telling you right there, the AP does that. They're going to give you something, and they're going to expect you to be able to look at that function and figure stuff like that out. Okay? Yes?
That means after a long time, though, wouldn't it finally keep dropping down?
It does keep dropping down. That's the question is, this does keep dropping down, basically, but there, and this isn't going to work, but, oh, it did. Asymptote. And as those values get huge, it's going to keep getting closer and closer to negative 2, but it is never, ever going to get there. It's going to get really close. That's the whole limit process. That's that limit process that's going to dominate calculus. It's never going to get there. Now, how about zeros, though? Now, I can't remember who I showed this little trick and who I haven't. I think in other classes we just kind of did something like this to find the zeros, right, just to get close. I'm going to show you a way to actually find it out exactly. No rounding needed at all. We're going to use this little blue one up here that says calculate. Okay? At least mine's blue. Yours is probably that, what, peach color or whatever it is, right? Orange or whatever. So it's the one right above here. So hit second and then trace. And what are we trying to calculate? Oh, a 0. Hey, it's the second one. All right. Now, the problem with that is, this probably won't work again, but all right. The 0 is right about there. Do you agree with that? Okay. It's asking for a left bound. So it's just asking for something that its x value is to the left of the one I'm trying to find. Do you agree where mine was kind of getting ready to blink there? Is it to the left of the point I'm actually trying to find? The x value. Do you agree it is to the left? Again, we'll get that out of here so it can actually work. So I want this one here. Is this to the left of it? Yes, it is. You could be way over here if you wanted to be. That's close enough. It's to the left of what I want. And do you agree there are no other zeros that could get confused with, right? So just go ahead and hit enter. Notice how it marked it up here with this little triangle looking thing. It marked the x value you chose. Now it wants a right bound. If I were to hit enter right now, is that to the right of the point I'm trying to find? No, so is that a good right bound? No, so how are you going to get over there? Hit it to the right. How about that? Is that to the right of what I want? Okay, how about over there? We're trying to hit the x-axis, remember? Is that, well, I'd go one more just to make sure. Do you agree that's to the x value is to the right of the one I'm trying to find? Are you in agreement? And what it's going to do is it will mark that one as well when you hit enter. You see how it has these two little triangles in here. It knows you've basically told it your 0 is in between those. All right? Now it's asking for a guess. You don't even have to do anything here. It does all the work anyways. So just say, yep, that's a good enough guess, close enough. Is everybody that far? Okay. When you hit enter, it will go and calculate that 0 exactly for you. Ready? And go. There it is. Exact out to 1, 2, 3, 4, 5, 6, 7, 8 decimal places. Which is way better than having to do all the other methods. Because obviously that would come from some quadratic, perhaps somewhere. There it is. And does it say where to round? Now we'll round out a little ways. So we'll say what? 0.631. Okay. So where do we go again for that? We obviously graphed it first, and where do we go to do zeros? Calculate, which is right there. Zoom, calculate, and which one? Obviously 0. These two down here, 6 and 7, those are calculus right there. That's why you don't know what. Well, you should know what this looks like. Okay. But that one you're not sure. That's fine. So you just go ahead and you hit that. You do a left bound, which means it has to be to the left of the point you want. Right bound has to be to the right of the point you want. It asks for a guess, but does it really matter? Not really. Not unless you're off in the boonies somewhere on one of your bounds. All right. As long as you're close, just hit enter again, and you're good. So is that a good one? Not really. So we go left bound, right bound, guess. Oh, hey, same answer. Okay. Because it actually calculates it for you. Yes? Zeros are where the graph hits the x-axis. Okay. Or the y value is 0. Any questions? All right.